In this video, I'm going to be going through what's new in large language models, these LLMs, and also some of the things to expect coming onto the horizon. Just recently, we've had ChatGPT come available for everyone to use, so definitely we're going to be talking about that too. So broadly, I'm going to talk through just a little bit about the basics of what these language models are, and then I'm going to cover three topics. The first of which is essentially how to make these things do what we want better, which includes reinforcement learning from human feedback, getting them to do reasoning and acting. So this is kind of an important thing, and in particular for InstructGPT and ChatGPT. And then I'm going to talk a little bit about a new research thing, auto prompt engineering, which is a cool thing coming, and also the idea of self-improvement, which is kind of one of the first examples where these models can actually teach themselves, which is kind of thrilling from an AI perspective. I'm going to end up on kind of a cautionary note to do with what can you really learn from language, then I'll just wrap up. Hopefully you enjoy this kind of content. Please give it a like and a thumbs up and subscribe. I guess all that YouTube stuff. Okay, so on to the basics. Now the models I'm going to talk about are mainly of the GPT variety, either kind of a GPT-3 sized, which is 173 billion parameters, or there's also the Google's Palm model, which is 540 billion. So these are enormous models which are trained to do a very simple task. The task is predict the next word. So if it's trained to predict next, it could be word, it could be big thing, it could be explosive growth area. Basically, there are a few choices for the next word, some more likely than others, but there are quite a lot of things which it probably wouldn't be. But in order to do that task, you kind of have to understand, in inverted commas, the whole context of whatever's coming up in the language which precedes it. So if you train this on a huge amounts of data, like Wikipedia is just a starter in terms of the amount of data. The entire text of Wikipedia would be a drop in the ocean compared to the amount of data these things are given. You'd actually get to understand quite a lot of text just by predicting the very next word. Now what we find is that we get the really interesting effects kind of kick in once we get to several billion parameters. Clearly that the really good results come up with the super large models. And what we find is that you can, with using Google's Colab, which would give you a T4 NVIDIA chip for free, you can already get up to like 6 billion parameters. And at that point, it's starting to get really interesting results. But as you go over 70 billion, which requires essentially special hardware, then things get really interesting. So in terms of prompting, we know that the model wants to continue the text, but it will do that kind of as it thinks that the internet would do that, continue the text. Now there's a whole lot of content on the internet, much of which is not appropriate, right? But rather than filter it ahead of time, people have tended to try and learn everything they can from every piece of text they can find, and then try and figure out, well, how do we make this better behaved? Now, this is clearly a problem if you're going to do dialogue with a customer. If you're a business looking to have a chatbot interacting with a customer, you don't want to essentially turn them on to 4chan type dialogue. You want to say nice things about the customer, or at least help them, rather than just abuse them. So the idea here is we're going to condition what the prompts are we're going to condition what the model says by prompting it how to answer, by essentially making it believe that the text it's generating is coming from a much politer area of the internet than average, right? So in that sense, what we're going to do is we're going to give it a prompt which helps it come up with something suitable for customer interactions. On the other hand, this is not really a control, this is just a good hint. And what people have found is that this kind of hinting works actually more generally than just where on the internet is this. For instance, an example of this would be the TLDR trick, where back in 2019 with the GPT-2 model, OpenAI found that if you gave it a news article, for instance, and then after the news article you say TLDR, the next token it will want to produce will actually start a summary of the news article it just read, because that's what people do with the TLDR output when they're writing on the internet in maybe a discussion group. So this TLDR trick is kind of a hint at how this prompting might work. Now this leads us to kind of the area of prompt engineering and kind of other shenanigans where people try and get these models to essentially demonstrate what they've learnt from the internet, but in a way which is much more useful for real use. Okay, so let's move on to the kind of main events of this year. There's been a lot of developments, one of which has been in this reinforcement learning from human feedback. This is the RLHF acronym, and people have also been playing with these models to try and get them to demonstrate how they're reasoning about tasks, and also getting them to try and act in the real world. So all of these things are kind of important pieces of a puzzle to make a truly useful interactive agent. So the basics of RLHF is basically we want to have the computer to learn what would be suitable for humans to interact with. And what I've done with these slides is that essentially these two pictures here are demonstrated by Stable Diffusion, where Stable Diffusion 2, which is shown on the right hand side, is actually a much more recent model than the Stable Diffusion 1.4, which came out in August, I guess, when this came out in late November. This is kind of showing for the same prompt what kind of images would you get out of each. So this is kind of like a sideshow demonstrating that Stable Diffusion 2 produces maybe better images for the prompt, but maybe less interesting images until people figure out how to make this work nicely. Anyway, this is a little demonstration of people prompting a text-to-image model to try and get the results they want. So again, this idea of prompt engineering is coming in through the images as well. Okay, so what we're trying to do with the reinforcement learning from human feedback is to try, and this is something kind of OpenAI has a nice blog post about, to do with aligning language models to follow instructions, and maybe it makes sense for us to talk through the process here. Okay, so the process takes part in 3 phases. The first is you're going to take a very large pre-trained model, basically trained on the internet, and then you give it examples of the tasks that you wanted to do. Maybe it's answering basic maths questions or doing a question answer task. Basically give it lots of labeled examples on how to do this task, and you basically train it up with the data that you've got. So the second step of this is you then get it to try to do the task on new instances, and you get it to try and generate several different examples of the output it should give. Now, we don't at this point know exactly whether it's going to get the right answer, but what we can do is get a human to label which of these answers is not just right or wrong, but in what order should we put these answers, or maybe there's an actual better answer it should have come up with. So basically this would allow us to label, this is the human feedback aspect, which of these answers are good, which are bad. So we then use this as the last step here to train what's called a reward model. Typically this is a smaller model, so not the big model we just trained in the first step, but a smaller model which learns to predict whether the human's going to think this output is good. Now you might think that, well, why don't you just train the big model to learn this output? The problem is that the big model will typically have way too much capacity to just learn the right answer. So what has been found is that actually a fairly small model is sufficient to capture what humans like and dislike about these answers. We can then use that model to then train up the big model. So this is what happens in the third phase, is we take the reward model that we just learnt, and we then feed in quite a large number of possible scenarios into the big model, get it to produce outputs, but then rate them according to this reward model. And basically there's a loop here where the reward model leads the big model to produce outputs or prefer outputs which are better as far as the humans would be concerned. So to put this concretely, suppose we want to have a nice dialogue engine. We could train first with step 0 is we would train from the entire internet, so it would know about language. We then step 1 we'd train it on lots and lots of dialogues. Maybe we'd look at interactions on Twitter between a person who says something and there's a response and then there's another response. Basically we take chains of responses and that would form some dialogue, like a dialogue data set. The second thing is we'd then say, okay, let's try and get lots of responses to a particular piece of dialogue or particular history, and then it would then produce a whole bunch of plausible next sentences, and we get a human to say, oh, I think this one's great, this one's, don't ever say this, kind of thing. And then having got that reward model trained, we then use it to then rate a whole bunch more dialogue, which is now essentially the reward model is training the big model, but it can do that at scale. So we don't have, because it's learned kind of what humans like and don't, it can then substitute in to train against a huge data set. So a simple example of this is it may require a very big model to produce lots and lots of different responses, but only a fairly small model to detect the fact that humans don't like racist responses. Right, so that you could imagine this reward model could be a racism detector, which would be a fairly simple model to train, but rather than essentially give my human preferences straight to the big model, which might just learn, it may just think it's a special case what I'm trying to tell it. Here the reward model would actually generalize pretty well from a fairly limited amount of data to then be able to teach the big model, like, just don't be racist. No matter what the situation is, this would trigger me as an anti-racist detector, literally trigger the don't do this reward, and that would enable the big model to learn from my human preferences on a huge data set. Okay, so now we've got the process kind of behind us, we can now have a look at the performance. So this graph shows for different model sizes going across the bottom how well these things perform for particular tasks, where basically can it follow instructions, that kind of task. So what we find is that the very big models, these GPT models, which can be enormous, if you don't give it any specific kind of hints as to what is required, this is essentially the performance you'd get if you just gave it the instructions and asked the internet, which is what it knows, like, what would you say next? The second line up basically is what happens if you kind of get it to prompt it to try and do your task a bit better, like setting the context a bit better. And yes, you can make the big ones perform much better, but it's still not as good as if you actually start to fine tune it. So suppose I had a big data set of how it should respond, and I actually try and encourage the weights of this model to respond well. But what we find is that this line on the top this is what happens if you give it the reinforcement learning from human feedback kind of training. Basically, we can actually make all of these models, so even the very smallest model would perform better than the biggest models, given this reinforcement training or this better training. So the references to the papers are all here. Basically, even with a small model, these instruct models, so instruct GPT, a small version of that will be better than the huge model without this kind of guidance. So what happened in the last few days is that ChatGPT was released, which was built on what's called GPT 3.5, which was kind of also news to the community, which has now become the default Da Vinci model. So the default huge model for GPT-3, which is an OpenAI model, has now been kind of upgraded. Unfortunately, that kind of invalidates lots of papers which just said we're using the biggest model which came before. Who knows exactly what data this was trained on? It's essentially closed, which is ironic. But now we have this GPT 3 model which has been upgraded, and ChatGPT is now an extension of that. So this is currently free to try out in terms of dollars, not free with an open source kind of capital F. And if you're interested in just seeing the results, then look on Twitter for like hashtag ChatGPT. Lots of people have got lots of interesting outputs from that. If you're going to try and use it yourself, which I would definitely encourage, it's super fun to play with, clearly the chats that you're going to put in will be used to further train the model. So you can see how this kind of preferences thing is going to be using your chats as you give it free data to train up the next version of this. Okay, so when you go to the link, if you go to chat.openai.com/chat, it's quite easy to find. You'll have to sign in, so basically you have to give it an email address and say you're going to use it for personal reasons. You'll get some OpenAI credit for the big model, but this actually doesn't use any credit. This is just a free model, free to use, free to play around with. If you start using it too fast, they might start to try and rate limit you. But if you're just interested in seeing what it will do, this is super interesting to play with. So I asked it, how does ChatGPT use RLHF? The first response it gave was it doesn't know about either of these things because it's just a language model trained by OpenAI. The second time I tried that, you can also see there's a count of the, like I just tried again. It actually knows all about reinforcement learning from human feedback, and it's quite instructive about how it works. Basically, you might have to play around with this, try and ask the right kind of question. But other fun things that people have been doing is trying it. Can you tell me that in a pirate voice or as a limerick? These are super fun things you can do. Okay, so let's now go on to the second of this kind of subtopic, reasoning. We got Rodin's thinker here. Can we get these models to kind of explain their reasoning? Because one clear problem that these models have is that they might give you an answer super confidently, but it will be the wrong answer and their reasoning might be terrible. So what people have found is that in order to get these models to do, say, mathematics well, it's very helpful to get the model to actually do the reasoning, and then it's much more likely to get the right answer, rather than if you just say, give me the number in the next word. Okay. So this came back, earlier in 2022. There's STAR algorithm from Google. Basically, it was essentially trying to let a model improve itself from learning from the reasoning that it generated. So the loop here, this is the algorithm, is we're going to give it a few examples of what kind of reasoning we're looking for. It's going to generate some new kinds of reasons. So like it's going to answer your question with a few different rationales. We're going to look at like which rationale led to the right answer, and that's a good rationale. That's what we're going to say. If it leads to the wrong answer, we're going to discard it, and we're going to try and get it to use these rationales so that it's eventually answers correctly a lot more. So in terms of diagram, basically we're going to go round a loop, putting the questions into a language model, getting some rationales. If the answers are right, we're going to use that, and then essentially going to keep using that in a kind of loop. There is another thing down the side here where we'd give a hint. I think to describe what's happening with a hint, I should blow this diagram up so you can see the scheme. So here's the same diagram but much larger. You can see that the question trying to be answered is what can be used to carry a small dog, and the answer choices are a swimming pool, a basket, a dog show, backyard, own home. Okay, so some of these are kind of nonsensical, but here the answer must be something that can be used to carry a small dog. Baskets are designed to hold things, therefore the answer is basket B. Okay, so that is a solid rationale getting to the correct answer. Now, if it were to get to the wrong answer, like there's a rationale which gave us, it thinks that backyard is a good thing to carry a dog, we'd say, okay, that was, we wouldn't tell it, oh, that was wrong. We'd just say, okay, that didn't work. What we then do is we'd put after basket, in brackets, we put correct in capital letters and give it the same question, but now the hint is we've told it what the answer is. So whatever rationale it's going to come to, hopefully it will feel like an idiot if it comes to the wrong answer. So this is kind of where this alternate loop with this hint is basically hopefully leading to another rationale with the right answer. So this enables us to get kind of more rationales, hopefully getting it to get to rationales which are sensible, basically by judging is it getting the right answer or not. Okay, so moving on from this algorithm, I guess one thing we need to talk about is a technique which came out a few months later called Let's Think Step by Step. This is from Tokyo University and Google. Basically, the idea here is instead of trying to force it to give us rationales by training it to give us rationales, why don't we just ask it for rationale? So here we'd say, in order to get the reasoning extraction, we'd give it a question, and then we'd start the answer off by saying, let's think step by step. And it's been proven nicely by the paper that if you just start the answer by let's think step by step, it will produce a nice little rationale and kind of come out with the answer. And then you say, and so the final answer is in Arabic numerals, and then the next word it would say would be the answer you're looking for. So this is kind of just a prompting trick, like the TLDR really, to try and actually expose rationales without kind of training it to do rationale processing. So this is, if the first way was kind of the white magic way of doing it, this is kind of the black magic way of doing it. Super nice. Okay, so now let's move on to the third part of this first topic, acting. So here we've got a computer dialogue thing acting in a play. Can these large language models learn to act in the real world? And this whole thing was inspired by a blog post talking about this whole topic. So one of the things which is identified is if you give GPT models, so these large language models, a Python interpreter, and explain like, how am I going to use this Python how do you use a Python interpreter? They can actually go and then make use of it themselves. Them I'm using very loosely. It can make use of it itself to generate the answers that you might be looking for. So this is a super powerful thing, because just by explaining how a tool could be used in the prompt, it can then go on and use the tool. So let me just blow up this picture and we'll have a look at that. Okay, so on the left, we've got essentially the prompt sequence. This is how you prompt these things to do this Python task. Basically, the first line is, your task is to answer questions to the best of your ability. You have access to a Python interpreter. So if you are not able to answer the question directly, you can write a program that answers the question. Okay. So basically, I think the way they do this, rather than fine-tuning the whole thing, is basically show examples of how you would invoke the Python interpreter, which is kind of like a markdown. You put up some quotes, and basically then you say, question, well, what is the current stock price of Tesla? And it then starts to say, okay, I'll write a Python program to get it. I'll use requests. I'll look at a URL, and finance.yahoo.com. It's crazy that this might work. You can also imagine this could be crazy dangerous, because it could also import OS, import system, blah, blah, blah. But basically you could write commands onto your real machine. Just executing these things is not a super great idea, but it is very interesting that this is possible. So the entire code for doing this, the Python code for doing this thing, is basically you use OpenAI, use their API, you ask the question, and then you basically look to output tokens, and then you use some indented code. And you exec the code. So this is the dangerous step here. You wouldn't want to sanitize it, or use a safer language than Python. But basically, this is, in terms of a thought experiment, this is extremely interesting because it demonstrates that these models are actually much more capable than you might imagine just by producing text one token at a time. It's actually learned to program to achieve goals of a programmer. So this is essentially Codex in autopilot mode. Okay, so next up we've got an example from Adept.ai. Adept.ai is a Silicon Valley startup, as far as I know. Presumably they've raised a crazy amount of money. And what they have trained is large language models with the capability of navigating websites. So here you would, using the neat interface, so they have a nice, if you go to their website, they have a demo, or a pre-canned demo, where you essentially they show how you would put in a query about, you're interested in a particular size house in a particular area for a particular cost. You would then use a realtor's kind of website to go through, put in some details about the property you're looking for and the area, price ranges, and then get back the results you're interested in. So this is kind of getting they're calling an action transformer, super interesting use case. There's another true reinforcement learning kind of use case coming out of DeepMind, where they have a robot virtual environment where you can actually prompt the robot to do tasks or please find this information, and it will then walk around this home environment picking up, using its essentially lightsaber, objects. Here we've said form a circle of objects in the pantry. So it has then gone off to the pantry through this environment, and it's now putting objects in a circle on the floor. So not only does it know how to pick up objects, manipulate them, but it also understands the concept of putting things in a circle. This is like this crazy kind of proof of concept that this might be interesting, might work. And these things will only get better, right, with time. In terms of interesting tools or interesting directions for programmers to go, there's this interesting line of work called LangChain. I'm not sure that this is necessarily the horse to back, but they're doing interesting work. They've also integrated ChatGPT. They're integrating lots of different tools into this, whereby you can tell you can write in Python, basically, here are the different properties that my language model needs to know about. And then as you execute your code, it can then call out to different routines to try and gather the information it needs. Maybe it'll pick off a website, read in a database, use Python to integrate the results, and do a bit of reasoning. Basically, this is extremely powerful, assuming you can kind of keep the different tools under control and they don't just decide to have fun kind of thing. As long as it's well directed, this is kind of very, very interesting in terms of acting. So there's an example here to do with trying to find out relationship between people and their ages and then do a mathematical operation. Nice examples. I'm sure there's even more examples in their GitHub now that ChatGPT's come along. And there's also some code released by Google, which is also talking about this kind of cascades of language model capabilities. This I haven't delved into much at all, but clearly, not only are open source people going after this, but also Google's have lots of these companies have this as kind of top of mind idea for try and compose different capabilities within these language models. Okay, so now we've gone through the chatting, the RLHF, rationales and acting. Let's go on to the second major topic here, which was prompt design. So I've mentioned quite a few of this kind of prompt engineering idea, but how do we come up with these prompts? And is prompt engineer a real job title going forwards? So this is an interesting piece of work, recent piece of work, saying, well, maybe these prompts could be rather than hand engineering them, which seems like a weird thing to be doing, maybe the computers could find the prompts for themselves. So the pictures here are a robot struggling to write a prompt at a computer. Basically, it's trying to capture the idea that a robot is trying to essentially program itself. So the kind of highlighted paper here is called Automatic Prompt Engineering, or APE. Basically, this has a very nice kind of site set up, and they've got a GitHub and a Colab you can play with. So the basic technique is outlined here, and it's kind of devious. So the prompt you give the model is, I gave a friend an instruction. Based on the instruction, they produced the following input-output pairs. And then you'd put the kind of thing you were interested in getting the model to do as input-output pairs. And then you'd say the instruction was to something. And at that point where this, brackets ape goes, the model is forced to come up with what is the next word, right? So the only way it can do that is by trying to give an instruction, because you've really led it down this path of how it would make those input-output pairs. So basically the input-output pairs are the task you want to do, and you're kind of forcing it to hand you back the instruction that would have worked. Okay, and then when it comes to using this, you basically say instruction with whatever it said. Here is like a demo using these pairs, and then you say, well, input is this, what is the output? And now the next word it comes up with kind of has to be led by its own instruction. So this is a sneaky way of getting it to come up with a variety of instructions. So you didn't just run this once, you'd run it several different times, and then each time it would come up with maybe different performance on a test set. And then you could say, well, I'm just going to automatically rank these instructions in terms of performance. So basically here we've got the model prompting itself to come up, and then your selection process basically boosts the ones which work really well. So here we have automatic prompt discovery, which the model can do, and the demos they have essentially interrogate, and you can do this demo yourself, the OpenAI GPT model, and they have in particular this playground and pricing you should have a look at before you start off with this. This is a way of essentially burning some of your $18 of free credit that OpenAI will give you. An experiment would typically cost like 60 cents, because even though individual quotes to the GPT-3 model are a couple of cents, fairly low priced, once you start to essentially engine by machine prompt to generate a data set, now the amounts of calls goes up. So this is something which you can definitely play with. It's super interesting to see the kind of prompts. Their demo includes selecting different kinds of data set to work with, and it has a price estimator, so you don't ever press go without kind of having an idea of how much it's going to cost. For this, you would need your own OpenAI API key, which you would get if you log in to try the ChatGPT. You'd also be able to get one of the API keys to play with $18 for 3 months. Okay, so now let's move on to the final of the 3 topics, self-improvement. So in terms of self-improvement, we've talked about learning from huge data sets, then fine-tuning on a curated data set, learning from humans by a human feedback thing, also trying to prompt yourself, well, getting the model to essentially rank how well it does on a variety of its own prompts. In terms of self-improvement, can we actually get the machine to teach itself? So this is a diagram of maybe the machine making itself. So the idea here, and this is the kind of early days of this positive trend in terms of machines teaching themselves, is, as we had before, maybe we could get the machine to produce multiple different reasoning paths. The idea being, what we would like to do is get a whole bunch of different rationales for how to answer the question. And before, what we did is we said, well, if it comes to the right answer, then the rationale's probably true. Here, what we're saying is, well, we don't actually know the right answer. What we're going to do is we're going to get it to produce multiple rationales, maybe 100 rationales, and if the model is originally sufficiently good, then the most popular answer is probably the correct answer. So this is where there's a kind of a tipping point. If you have a small model, it might produce such a spread of weird answers that there's no consistency, or it may just be consistently wrong answers. But as you move up in terms of the size of the model, beyond a certain interesting point, these models will be pretty consistently right, maybe 60% of the time, but wrongly, lots of different diverse answers, diverse and wrong answers for the rest of the time. But because they're producing stuff which is somewhat consistent, we can then say, or the idea behind this paper is the ones which are consistent are probably true. So what we're then going to do is use that and say that these are true reasoning and put that into the data set. So this actually increases the size of the kinds of reasoning that the model will be able to do, because it can then fine-tune to be able to answer this again, not just this question, but be able to reason better the next time around. This paper was submitted anonymously, but the fact that it's got this 540 billion parameter model, which is clearly a Palm model, it kind of limits the number of people who could have written the paper, which is good for them. I guess makes everyone else feel a bit green with envy. Now, the reason that this kind of works is one of the key elements of this is that we actually find that the models actually are the more right they are, the more confident they are. So once the models are big enough in size, they turn out to be kind of well calibrated, in as much as if they're kind of confident about the answer, and you can measure this by looking at the probability of what they just came up with, you can then say, well, the more confident it is, the more likely it is to be correct. And if we take lots of samples of this, then and pick them, rank them or whatever, we can actually come up with things which are correct more often than not. I guess, and it's also important to say that this kind of technique has been well known for quite a while, in that you can even do this kind of pseudo labeling or pseudo training with MNIST digits. Suppose we take just half of the MNIST digits, like a smaller data set, get it to try and label some of the unknown digits, and then pass those which it's confident about into the training set. We can actually get like a small amount of human trained data and leverage it up into a bigger training set. So even this idea kind of works for really small models. The fact that it works for complex reasoning tasks is super interesting. So here's a diagram of how this works. Let me just blow this up so you can see it more clearly. Okay, so here's an example of a prompt on the left hand side. So this is John buys 20 cards and a quarter are uncommon, and then basically these would be chain of thought reasoning. This is COT, chain of thought. Here's some kind of rationales and answers. So basically you give it like a little template about what the kind of thing it should do. Here's a final question, and the answer is, okay, now generate a bunch of rationales. So here we've got Amy is 10, Jake is 8, Alex's age is right in the middle. Hopefully it's going to say Alex is 9. Okay. So here it's Alex is 10 minus 8 is 2 years old. Okay, that's not a very good answer. Alex is in the middle of 8 and 10. Alex is 9. Okay. So basically here's a whole bunch of different rationales by running the LLM multiple times. This is a multipath decoding. You're basically going to say, well, which are the most popular answers? And then the most popular is probably the right answer. Okay, so we're not, before with the star method, we were just choosing the answer which we knew was right to inform us of the best rationales. Here we're just saying the answer which is most common is probably right. And here we then take this data set and then add this to the training data set. Once we've come up with what we think is the right answer, we then use that to train even more, to make this hopefully more robust in terms of its training set. Now, one of the downsides of this could be that if it starts to answer things wrong, it would then put wrong answers into its data set and get even more wrong. So there is a kind of a negative cascade that could happen. But fortunately, what people have found, certainly with the big models, is that this cascade actually is a positive reinforcement loop, enabling these models to do better than the original training data. Okay, so in terms of results, how does this work particularly well? Well, we've got two panels here. The top of them is basically looking at how these models work without having this self-improvement idea, and you'll see that for all these different tasks in the columns, we're getting pretty good results. I mean, these are big language models after all. But if you then add in this self-training idea, we're now getting to much higher results down here. So the first these three in each batch, the first of these is kind of the standard prompting. Particularly if you look at this GSMAK task set, we've got 18%, 56, 74%. So basically standard prompting, chain of thought prompting, and then self-consistency, which is, I guess, like the star. Basically this is coming up to 74 kind of numbers, using this self-reinforcement kind of thing going on. Looking at the standard prompting, we've increased from 18 to 32. From the chain of thought, we've increased. The self-consistency increased even more. So basically all of these things is doing this self-improvement, which is the model training itself, is working out. And I guess another interesting thing from the paper is, suppose we were to train use these models without the special reinforcement learning, to use these on these different size models. We've got some good results on the 540 billion thing, but if we distill these models down into smaller model sizes, we can still retain quite a lot of the performance. In fact, for the 62 billion from this, so this is, I guess, 9 times smaller, we've actually improved from the big model. But even if we take it down to 8 billion, which is getting to a place where we could use it with tricks on just a regular GPU, basically, if we distill a huge model down into a smaller model, we can actually retain quite a lot of the performance. So where, in order to get this self-reinforcement thing working well, we need a huge model. But once we've got that working, we can now transport this into a smaller model and retain the benefits. So this is a very interesting direction to go. So these are clearly just early results. The idea is somewhat simple, but clearly there are implementation issues that you have to get over. But it's also possible that this could be workable on smaller and more accessible models from the get-go. Since this is early days, it makes sense to play with the huge models, but maybe this is approachable by many more people. I would love to see that happen. Okay, so one cautionary note, which I mentioned right at the beginning, it's coming from Jan LeCun, with a co-author, had a nice blog post called AI and the Limits of Language. The issue that they're trying to address is, can a large language model trained only on words learn everything that you would need to become generally intelligent? And the answer that they're coming up with is basically you can't learn everything you need to know about the world from the written word. Now, they have a variety of kind of arguments about why everything that needs to be known about the real world isn't written down or is difficult to kind of explain. in as much as can the models understand the real world just by reading words about the real world. I guess another kind of issue is much of what's going on in the real world isn't really written down. So suppose we're talking about the effect of gravity on objects. If it's what normally happens to objects, people just don't bother to write down what happens because of gravity. Things will just fall off tables, or things will roll on the table and then smash on the floor, right? There's a missing step in there which people don't have to bother to describe, because it's what happens in the real world. In fact, if you think about lots of science fiction stories, they'll talk about things which happen in the absence of gravity. There'll be a lot of focus on stuff which is not the normal case. So a lot of common sense isn't really written down. So this is not really something which they talk too much about, but you can kind of get the gist of some of the problems that might occur with the written word. On the other hand, if you could integrate like other media, like photos or films, suddenly you've got a rich source of other truth about the real world. So maybe this kind of points us that these large language models should also be addressing YouTube videos to find out what really happens to cars as they drive, or all sorts of things you could learn about the world which wouldn't necessarily be written down in huge detail. So this is the caution note, a nice blog post to read, just in case you thought that AGI is going to be achieved just by reading words. This is saying, not so fast. Maybe there's stuff that would need to be, if not directly experienced in the world, would need to be absorbed by either watching it or listening for it in order to get proper experience. Okay, so in terms of wrapping up, we're quickly finding out, this has all happened like this year, how to control these large language models. Fortunately, they're not ready to take off and take over just yet. Hopefully we'll be fully in control the whole time. What would be nice to be able to see is a stable diffusion-like explosion of creativity and innovation which has happened. So stable diffusion, the text-to-image model which came out and was fully released, enabled huge numbers of people to experiment with these advanced models, and the pace of innovation just because of that has alarmingly outstripped these big research labs, just because there's lots of people doing lots of interesting things if you get the tools into their hands. So it will be super interesting to see what would happen if we can get some of these large or essentially equivalent models to be accessible to a very diverse set of people. We could hopefully get a lot more innovation going on, even though the pace of research at the moment is incredible. So I'm keeping my fingers crossed for more access to more people, for more innovation to come. Okay, so hopefully you found the subject interesting. I hope to do more videos as time goes on. Maybe I'll do something on Minecraft, which is a competition which just happened at NeurIPS. If you're in Singapore, please feel free to drop into our machine learning meetup group. We've had online sessions during the pandemic, but now we're fully back in person. Our next meeting is probably in January. Hopefully we'll do like a NeurIPS roundup, so that people can get the flavour of what's been going on in research world. This is often a popular thing that we do once a year. Hopefully see you around in the next one.